All right, these are page 2 of the notes 3-5, rational functions. And so this first part is dealing with, you know, sort of the rules that help us determine where our vertical and where our horizontal asymptotes are. And then we'll talk about a special case of a hole, and we'll see that in some of these examples down below. All right, so vertical asymptotes. And then also sometimes instead of a vertical asymptote, we have a hole. But they arise at an x value that makes the denominator equal to 0 in the original function that they give us. All right, so as x gets closer and closer to some a value, then f of x, the function, is going to approach infinity, or it's going to approach negative infinity. And so then if that happens, then x equals a is going to be the equation of that vertical asymptote. So if we get closer and closer to some value a, the value of the function as x gets close to a, so you can't say f of a because that'll make it undefined, but as if x is getting closer and closer to a and f of x is getting closer and closer to either infinity or negative infinity, then that means there's an asymptote at x equals a. Okay, and so x equals a would be the equation of that vertical line, which is the vertical asymptote. Okay, and again, we don't evaluate f of x at a. We can't just plug a in because that doesn't exist. All right, so it doesn't make any sense to like, oh, well, let's just see what it's like. But no, can't do that. All right, and then we have special case when we have a hole. So if we have a binomial x minus c is a factor of both the numerator and the denominator, that means that we would cancel it out. And then as a result, we no longer have like this badness in the denominator. And so that means a value of c no longer makes the denominator 0. And so it kind of looks like we're okay, but we are asked to graph the original function, not the simplified function. And so this still makes the original function undefined. An x value of c would make part of the denominator 0, and it's a factor, so it would make the whole denominator 0. All right? We'll do some examples, and it'll make more sense at the time. So that what happens when part of the denominator cancels with part of the numerator and sort of like looks like a badness, an actual x value that would make it undefined disappears, then instead what we have is we have a hole there. So at that x value, where it would have been bad, but it canceled, so it kind of seems like it's okay, there'll be a hole if we plug c into the new reduced function, f of x. Right? And so f of c, we're calling this reduced one with a little asterisk to differentiate it between f of x. So this is like the reduced one after we canceled out the binomial upstairs and down. Then we'll plug c into that reduced one to find the y coordinate of the hole. Again, this is all very theoretical, so when we get to an example, it'll make more sense. Okay, so we will not have a vertical asymptote at c in this case. Instead, we'll have a hole. All right, it's only when part of it, when that binomial cancels with the same binomial upstairs. Okay. So, but don't worry, that it sounds really confusing, but when we go through an example, it'll make more sense. All right, the horizontal asymptotes. So they're a little bit more difficult to visualize sometimes. So horizontal and sometimes oblique asymptotes, we'll talk about those when we get to an example of it, are found by considering what f of x approaches as we let x get either really big or really small. So as x approaches infinity or x approaches negative infinity, so as x gets really big or gets really small, then f of x approaches some value, then that means y equals that value b. is going to be the equation of the horizontal asymptote. So there's a couple of cases. So one, if the numerator has a degree less than the numerator. So for example, that would be like what we saw before, 1 over x. The degree upstairs is 0. The degree downstairs is 1. So the numerator has a degree less than the denominator, and that was the very first example we did on the first page. All right, that means as x gets really big, this whole thing is approaching 0. All right, so that means y equals 0 is going to be the, and even if it's negative infinity, if it gets really big in the positive or negative direction, the magnitude of 1 over x is getting smaller and smaller. It might be negative, it might be approaching it from the bottom or from the top. So the asymptote, the horizontal asymptote, will be y equals 0. All right, if the number of the numerator and the denominator have the same degree, so that would be like x minus 2 over x plus 1. They both have the same degree. Then the equation of the horizontal asymptote is simply going to be the leading coefficient at the top divided by the leading coefficient at the bottom. So in this case, it would be y equals 1 because it's 1 divided by 1. All right, so it's when the degrees are the same. It doesn't matter if it's 2 and 2. So long as the degrees are the same, the leading coefficient divided by the leading coefficient will give us the equation of the horizontal asymptote. Okay, so that's the first two cases. The third case, if the numerator has a degree that's exactly 1 more than the denominator. So that would be something like x squared over x minus 1. Right? The degree upstairs is exactly 1 more than the degree downstairs. So this has a degree 2, this has degree 1, exactly 1 degree more. Then we're going to have an oblique asymptote. So we're only going to require that you understand how to deal with these three cases when we're graphing. So don't worry about like, well, what if it's something else, right? So if the degree downstairs is higher than the degree upstairs, and it doesn't have to be by 1, it can be anything, right? X cubed, 1 over x cubed. So long as the part A is that the degree downstairs is bigger than the degree upstairs. Case B is that the degrees are the same. And then case C is the degree upstairs is 1 more than the degree downstairs. All right, then we're going to divide the numerator by the denominator, using like synthetic division if we can. The depressed polynomial, disregarding the remainder, is the linear equation of the oblique asymptote. So what we mean by oblique. So the asymptote is not going to be horizontal, it's going to be at an angle, or oblique. Okay, so let's look at some examples. All right, number 4, A. So the first thing we want to do here is probably see if we can factor this, right? So because if it's factorable, we might be able to cancel out part of the numerator with part of the denominator. So that's definitely what we want to try to do here. So we have x minus 2. We have what? X, and looks like what? Minus 3 plus 2. All right, so we don't have any like binomials that we can cancel. And so what we want to do here is we want to just find the equations of all the asymptotes. All right, so vertical asymptotes, let's start with that. VA, vertical asymptotes. All right, are there any vertical asymptotes? Are there any bad x values? Are there any x values that would turn the denominator 0? So those would have to be eliminated, and those will generate vertical asymptotes. All right, so we get x equals 3. Don't write down just 3, write down the equation. X equals 3. Any others? X equals negative 2, right, is the other one. And then horizontal. Okay, so which case do we have? Case A, B, or C here. The degree upstairs is smaller than the degree downstairs. So our horizontal asymptote, according to case A, is y equals 0. Which makes sense. If x gets really, really big, say it's $1 billion, right? The bottom is getting really big even faster. It's 1,000,000,000 squared. So we can think of it as almost like 1 over 1,000,000,000, which would be 0. All right, it will approach 0. Won't ever equal 0, but it'll be close to it'll get smaller and smaller and smaller as x gets bigger and bigger and bigger. All right, B. All right, is there anything, well, we could factor the top, but that's just going to be what, 2, and then 2x minus 1. So that doesn't cancel with anything downstairs, so probably we don't really need to factor that. Vertical asymptote. Is there any vertical asymptote? All right, x equals -1 is the vertical asymptote. And then any horizontal. Well, let's see. Think about the horizontal. Which case is this? Is this A, B, or C from up above? And it looks like B, right? The degree is the same. So the horizontal asymptote will simply be y equals the ratio of the leading coefficients, 4 over 1, or just 4. Okay? All right, let's go down to C. All right, anything to factor? Well, yeah, we could factor this. This would be x and x plus 1, but that doesn't cancel, so factoring isn't going to help us here. All right. Do we have any vertical asymptotes? Looks like we would have a vertical asymptote at x equals 1. Now let's contemplate the horizontal asymptote. So the horizontal asymptote, the degree is higher than it's 1 degree higher than the denominator. The numerator is 2 degrees higher. It's 2, and then the numerator is 2, the denominator is 1. So it's 1 degree more. That's exactly case C from up above. All right, this case C. So that means we need to divide the two. All right, so it's a nice binomial, so we can use synthetic division. Let's see, we're going to put a 1 in the box, and next to it we're going to put a 1 and a 1, and we have a missing term, 0, which is the constant, so we'll put that in, and then we'll do synthetic division. So we bring the 1 down, we multiply, that's 1, add it to this 1, that's 2, multiply, that's 2, and add, and that would be 2. So it's the depressed polynomial ignoring the remainder. So the horizontal asymptote, actually it's not horizontal, it's an oblique asymptote, right? The oblique asymptote will be y equals, and write this equation, x squared, nope, sorry, not x squared, just x to the first power. So x, make sure I get rid of that, square x plus 2 is the equation of the oblique asymptote. Okay? And we'll practice graphing those, but, so that's going to be, x plus 2. So it's going to be an asymptote up here, right? And then we'll have a vertical asymptote at 1. And then, it's either, what will happen is the curve will either be out here and here, or, see if I can find a colored pencil here, or it will be in here and in here. So you just got to plot a couple points and to kind of figure out what it's going to be. All right, so that's the kind of the options when you have this oblique asymptote. All right, but we'll practice more. I think on page 3 has us graphing a couple of these. All right, and then let's look at this last one. So let's see if this factors. The top is a difference of squares, so we could say x plus 2, x minus 2. And on the bottom we have x minus 2. So to start with, we look at this and we say, oh, the vertical asymptote looks to be like it's going to be x equals 2, but it's not. Because that x minus 2 cancels with that x minus 2, leaving us with a reduced function of x plus 2. All right, so this function is going to look exactly the same as this function, except there's going to be a hole. So at this point where the denominator, the original denominator would have been 0, so at x equals 2, we don't have a vertical asymptote. Instead, we have a hole. And so a hole, that looks more like an equation than a hole. A hole is going to be a point, and so we'll say 2, comma, and then we need to find the, so we won't say x equals 2 is the hole, we'll say where's the location of that hole, or where's the point that's missing from the graph. And so we'll say 2, comma, and then we need to find this, essentially f of 2. But the problem is we can't put 2 into the original function. We put 2 into this reduced function. So this new function, evaluated at 2, would give us an output or y value of 4. All right. So let's think about what this line looks like. It has 1, 2, right? Y-intercept of 2, slope of, looks like 1. So something like this, let's say, except at the point 1, 2, like, okay, go over 2, we're up here. We don't have that point. That point's not there. There is a hole. Okay? So that hole occurs at 2, comma 4. So this graph looks exactly like this graph, except we need to include the hole with this thing. All right, and so because they didn't ask us to graph this function, they're asking us to graph this original function, and x minus 2 is not defined, and x value of 2 is not defined there, and so that's what ends up getting us our hole. Okay, so we've talked about sort of vertical versus horizontal, oblique asymptotes, and situations that involve a hole. Okay, and then also look at, think about, do we have any kind of asymptote here? We don't. There could be a case where, like, maybe the bottom, after we factored this, like, let's say we have x minus 2, x plus 3, and then we have x plus 2, and x minus 2. Let's say that was the original function. We factored it. These went away. Then, this was a nice line. The reduced function here is x plus 3, is another asymptotic function, not just a simple line, right? But it will have a hole at an x value of 2. Plug a 2 into this to help figure out where the y coordinate for the hole would be. So that would be something more like, I'm just sketching it quickly, something like an asymptotic function like this, but it might have a hole in it somewhere. All right, so that's kind of what you would have here. Holes are not just going to be simple holes on lines. You can have more complicated curves with a hole in it. All right. Of course, don't draw the curve through the hole. That would be silly. You want to erase, the curve as it goes through the hole, and make sure that it's empty inside. Don't have your line showing up through there. Okay. So that was page 2.